Hi, it is my pleasure to host the QuakeCoRE seminar series today. My name is Santiago Pujol. I'm the director of QuakeCoRE. And today, our guest speaker is Dr. Ashkan Hashemi, who's a senior lecturer at the University of Auckland. Dr. Hashemi received his PhD from the same institution, and he's very well known throughout New Zealand for being an innovator. He's produced a number of devices, dampers mostly, that are being used out in practice. And in that sense, Dr. Hashemi is also very well known for creating very good connections between academia and industry. And for that reason and many other reasons, Dr. Hashemi received the EQC NZS EE Ivan Skinner Award. Today, Dr. Hashemi is going to talk to us about CLT, Cross-Laminated Timber, which in many ways, in my mind, is the material of the future. Before I yield the floor to Dr. Hashemi, I'd like to remind you that you're very much welcome to type questions on the chat. After Dr. Hashemi is done, I'll read some of those questions, or I'll invite you to ask questions directly. So with that, Dr. Hashemi, the floor is yours.
Thank you, Santiago, for the introduction, and thank you everyone for joining the webinar. So today I'm going to kind of summarize and report on the recent test that we did on a full-scale two-story cross-laminated timber structure at the University of Auckland. And then the outcomes, conclusions, and hopefully we'll have good discussions at the end. Before we go to the presentation itself, just wanted to emphasize that this research is directly relevant to the disciplinary theme 2 of QuakeCoRE, whole of a building seismic performance. You know, we researchers sometimes, unfortunately, we tend to research and test on individual components of structures, buildings, or so, without fully understanding the implications of several structural components working together as a system. And I think DT2 within QuakeCoRE did a great job of emphasizing on that and kind of supporting activities towards that. So that's the story of our research as well. If we want to talk about the research background, it started like 10 years ago, and incrementally we developed parts of it, we tested parts of it, but we finally were able to test it as a building and to understand how does it behave as a three-dimensional building as close as possible to reality. So a little bit of why mass timber. So what is actually mass timber is, you would understand better the meaning of mass timber when you consider light timber framing or the type of traditional timber construction. Most of the houses in New Zealand are made with that. As opposed to that, we have mass timber, which is timber boards going into the factory, processed, pressed, and glued, and they come out as in different forms and shapes, like panels or beams, columns, and so on. So we call them, we call them engineered wood products in New Zealand. Everywhere else in the world, they're calling them mass timber elements. So in that sense, we are unique, but EWP or engineered wood product is the same, has the same meaning as mass timber. So why we use them? Construction time, reduced construction time, the weight is significantly reduced, and then you have a very great capability in terms of flexibility in terms of different products available, and it's safe and durable. Fire is no longer an issue, and obviously it's sustainable. For New Zealand, we have one of the best structural wood in the world in New Zealand, maybe the best. And also it's a kind of only renewable construction material. So and also architectural finish is favorable. Well, it's really not nice to look at timber elements. So for all these reasons, and also mostly the carbon target, net zero carbon target of 2050 that the country has, we're seeing a bit more interest in towards mass timber being used. But mass timber has a kind of a problem when it comes to earthquake-prone areas like New Zealand. Wood is a brittle material, although it has some ductility in perpendicular to grain, and I'm doing a research as we speak to understand if we can even utilize that towards seismic protection or not. But common sense is timber is brittle. We want ductile structures. So how do we get it? We get it through connections. Traditional connections within timber are like the ones you see, steel brackets plus fasteners, could be nails, screws, bolts, or rivets. And they perform not great under cycles of loading, unloading. They will pull out and the timber around the fastener will crush.
Ashkan?
Yes?
I'm sorry, we're not seeing your slides.
Oh, no?
Oh, I'm sorry. Sorry, we are. I was looking at the wrong screen.
Okay. Okay. Sorry. Okay. Yeah, so the performance of these connections are not desirable. Here you can see after 4 cycles of loading, almost 0 stiffness left in the system. So that's why we call timber structures made with traditional connections sloppy. And we try to resolve that. And you can see more examples here. These are very recent examples from either tests or observations after earthquakes. And the failure modes, regardless of being brittle or ductile, in terms of functional recovery, in terms of desirable seismic performance, it doesn't matter. If it's brittle, it could be catastrophic. Even if it's ductile, like this one, still the structure wouldn't have the same capacity as it had before the event. So with our research, we try to address that. For example, one important aspect is the wall-to-floor connection. If you use a traditional wall-to-floor connection like this, then after earthquake, these fasteners will yield, will pull out, and the timber around there will crush. The damage is irreparable, and I don't think there's any way to efficiently repair the connections. One thing to add is that in mass timber structures, all timber walls are rocking walls because you can't have cast in place like concrete timber walls. So there is always a hold down connecting the wall to the foundation. Now, when looking at system performance, with rocking wall structures, there are 2 kind of concepts usually done before in mass timber space. One is conventional hold down, some sort of hold down used at the base to control the rocking behavior or kind of control the moment resistant capacity of the wall, and also the rocking walls with post tension cables, which this was developed at the University of Canterbury years ago, was using a post tension element up the height and using some sort of energy dissipator or dampers at the base. So obviously the latter shows a much better performance compared to traditional timber walls. What we try to do for our research is to, first of all, remove the post-tension element up the height. And we had several reasons for it: practicality, the shrinkage in timber, and so on. And then understand if we can get what we want from having the hold downs at the base, also having sort of a damper in between walls, sort of encouraging the coupled wall mechanism. So that was one of the objectives in this research. So before going to details, just wanted to describe the motivation. We want a resilience design. We wanted to get rid of post-tension elements. We wanted to test at full scale. We wanted to look at displacement compatibility everywhere, wall-to-floor connections, column-to-column, column base, and so on. And then we wanted to incorporate everything we learned from previous research into this one. We had to start somewhere. So we looked around and we realized that the FEMA P695 probably would give us the best framework so we can have a big picture view of the research. So we kind of went through that for this research, but we had to divert here and there to make sure everything works. But basically, that was the procedure we followed for the research. This is our test specimen. So we call it full scale because it had 2 stories, 3 meter high and 6 meter wide. This is the biggest we could fit in the lab. So obviously it's not an actual building, but it's as close as we could get to an actual building in terms of dimensions. And we used CLT panels as walls and floors, columns, and beams. So everything is cross-laminated timber made in New Zealand. Currently, Red Stag is the only kind of fabricator of CLT in the country. And then all of these are made of New Zealand radiata pine species. The test setup included 2 different lateral mechanisms in the 2 orthogonal directions. In one direction, we had rocking walls, as we discussed, with self-centering hold downs at the base, with flexible wall-to-floor connections, and with a coupling damper in between. So we took a hybrid approach. We used balloon framing method for the walls, which means the walls are continuous, but we took in a platform framing approach with the gravity columns, which means the columns were not continuous and each floor was like a platform that the next floor will build on it. This is a very common approach in timber construction around the world. In terms of designing the specimen, we kind of had to look at everything. As many of you would know, there is no actual design guideline for such buildings. So we looked at whatever resources we could from different suppliers of fasteners, from the CLT handbook from FP Innovations from Canada was a great help. Also our own standards, using ETABS a lot, and using Autodesk Inventor to create a sort of a similar to a BIM model for the structure to be able to look at everything in one place. And in terms of designing the connection, that was the kind of the most challenging part because there is no common detailing for such structures. So we had to kind of adapt and look at the literature and see what can be done. And kind of we used the knife blade approach for different connections. This is most common in North America, and then it's done in New Zealand as well. But then we had to adapt, we had to innovate in that space as well, because as I mentioned, we've been using for the first time, I think, CLT beams and CLT columns, as well as walls and floors. So we had to kind of develop some finite element models for each of these connections to make sure they behave as they have to. In between the walls, we also used friction dampers, and I'll explain in a bit that how they kind of improve the behavior of the system. So this is the load deformation behavior of the damper that we put in between the walls, and you know, all of the energy dissipation devices, everything we put in, we put on the test before it goes there. We did like a component testing to make sure that they're calibrated well as per the specifications we wanted. And we kind of used a rocking wall system in plane and brace frame in out of plane. We had to make sure that the columns can rotate, are flexible, can rotate in and out of plane or up to 4% without significant damage to the column base. And again, emphasizing it's not like a steel structure that we can yield anything. We had to make sure that more or less everything remains elastic while the structure moves. This is the type of damper we use at the base of the walls, which this is the one that I myself tested on a CLT wall like I think 9 years ago. But we have never tested it in an actual 3-dimensional specimen. And this is the result of the component test. And then for the corners of the rocking walls, based on the recent research done at Lehigh University in the US, we realized that unless you reinforce the rocking toes of the system, you're going to see some crushing that's going to accumulate over time, and it's going to create problems down the road. We observed the same thing. If you don't reinforce, you'll see something like this at the rocking toe, even if you kind of use a screws or something to reinforce it internally. You need to have some sort of pocket, steel pocket at the rocking toes. So we had the same observation as Lehigh, and we adopted the same approach, and it worked fine. We started a test with a snapback test. We basically pushed the structure and let it go. And from there, we could kind of make sure that the system performed well, and it provides the behavior we want. In terms of the testing protocol used, we adopted the testing protocols from FEMA 461, section 291 and 292 for in-plane and bidirectional loading. For the bidirectional tests, we subjected the structure to 2.5% drift in the 2 directions. And then for unidirectional tests, we went up to 4.1% drift. Some of the test results are here. I'm going to show you some videos very, very shortly, but basically we pushed the structure to different levels of drifts, and we monitored the performance, low deformation behavior of the system. And we actually didn't observe any of the issues that a conventional timber building would have. No pinching, no loss of strength and stiffness over time, and no, more importantly, no damage to any of the connections I described. So in that sense, it was a bit boring because we didn't see any failure anywhere to report on, but overall it behaved as expected. And out of plane, we had these ductile tension bracing system. Again, we saw what we expected to see, a flag shape low deformation performance. So this video just quickly shows how the system moved for in-plane testing. This is about 4% drift. And I'll show it again. You can see the way the walls move and rock and the way that the coupling damper actually works. And this shows a snap view of the bidirectional testing that we did to 2.5% each direction. And again, all of the connections, column to column, beam to column, and wall to floor connections behaved as they should have. And a view of the coupling damper. Yeah, video has some issues, I think. So with this coupling damper used in between the walls, we kind of lost the fully self-centering capability of the system, but it added to the damping in a way that you could get the maximum possible ductility out of the system. I understand this is important for practice, that how much ductility you can get from the system. From the system, you can get something between 3 to 4, which is kind of the maximum you can get from any system. And also a closer view of the hold downs and the rocking behavior of the hold downs. So the benefits of the system, if you want to summarize it, is, well, low damage design. There was no yielding or crushing in timber. Ductility was high, as I mentioned, because usually for conventional timber construction, you have ductility of 2 and then over a strength factor of 2, which basically, if you want to design a ductile timber building made with traditional connections, you kind of have to, although the design is ductile, but you kind of need to work with elastic forces. Energy dissipation significantly increased compared to conventional timber construction, and you have self-centering and you have lower drifts. So this is conclusion of the first part of the presentation. Design process, a simple design process for the system, efficient use of timber, high ductility, low damage, and then full-scale verification. And also for the first time, we use CLT columns and beams, which means lower cost compared to other types of wood you use for columns and beams like LVL and glulam, which contributes to have more economy. Yeah, so the last part of the presentation is about the wall-to-floor interaction of timber structures. And I explain at the end why I've divided the presentation into 2 sections, but basically with conventional design, you would have a system like this, and then when the wall wants to go up, the floor doesn't want to go up, and then you'll have damage at the wall-to-floor level. So this was several times observed in different timber structures, either in test or observations following earthquakes. So what we try to do in this research, to use it to test, basically to come up and test 2 different types of connections at the floor to wall level that both of them solve the problem, which means decouple the floor from the wall vertically so the wall can move up and down without any problem. And at the same time, they stay coupled horizontally, which means the shear loads kind of transferred efficiently. So I'll explain what we did here. So in terms of wall-to-floor connections, we use a kind of a innovative shear key at the wall-to-floor connections and also at the base. And also we introduce some, we call it side dampers, to the sides of the wall at the wall-to-floor connection to see if these would improve the sizing performance of the system or no. As I described before, everything component tested before going on the specimen to make sure that everything performed well. So the type of shear key we use at the wall-to-floor level and also at the base was, the difference was it is a bolted connection, but the holes, instead of being like a common slot, it's like a heart-shaped slot, which allows the bolts to move on the edges of the basically the slotted hole with a pattern adapted from the movement of the wall. So this way they won't jam and the wall can move up and down efficiently. Same protocols that we use for in-plane and out-of-plane testing I describe we use here. And the low deformation response was great, again, in both directions. The ductility factor of 3 was achieved in both directions. Now, looking closely at the shear key performance, so this is at the center, this is at rest, and at left and right, you can see the pattern of the that the bolts of the shear key would move. And with this way, we made sure that the wall can rock. And at the same observations, the 3 images at the bottom shows the same observations for the wall-to-floor connections. So this way, the wall could go up and down without damaging the connection, which is a major problem usually for timber structures. So this video quickly show that what I mean. As you can see, the wall rocks and displacement compatibility is provided. In terms of the side dampers that we discussed, so here the results with and without the side dampers are shown. Like it generally not much difference, but ductility was increased by factor of 1, which means like 2.5 increased to 3.5. So the point is, at the times that you need a little bit damping in the system, this is a very efficient and cheap way to achieve that. Shear key effectiveness, displacement, opening of the hold downs and the wall-to-floor friction dampers closely match. So if you look at these curves that are kind of closely matching each other, you'll notice that there's almost no difference, which shows that the rocking, pure rocking behavior was achieved. And these are after all the tests, which we kind of applied the loading protocols more than 100 times. You see that there was no damage to the holes, to the wall, to the fasteners. There was no crushing of timber, more importantly, around the holes, which was great. And the same for the wall dampers. There was no sign of timber or bearing failure anywhere, which was great. Okay, now this is the last part of the presentation. We also tested a single dowel shear key. So instead of using a multi-dowel wall-to-floor connection, we use a single dowel wall-to-floor connection as well. The reason we did it is that there's research done in Canterbury a few years back by Daniel Moroder, and that showed that the single dowel wall-to-floor connection works fine, but the multi-dowel one, the one we tested, had some jamming issues. So we kind of tested both to compare. The single dowel concept also, as expected, worked fine. You can, this is from the top of the specimen. You can see the wall can go up and down without any problem, and then the shear was transferred efficiently through the single dowel shear key as well. The key thing was we observed similar behavior for both types of shear keys we used, and appreciating that the multi-dowel or the bolted connection shear key is cheaper to make and it's more common to adopt in practice. The performance with and without the side dampers shows a bit of difference in damping and ductility. As I mentioned, this is a great way of achieving higher ductilities in places that we are very limited in drift, like there is a neighbor building or something. You cannot go beyond, like, for example, 1% drift, but you need the damping and ductility at 1% drift. An efficient way to achieve that is using the side dampers at the side of the walls. So that's the end of the presentation. I'd like to especially thank Sohail and Setu, the two PhD students who worked 8 years combined on this project, and they're about to submit their thesis. Maybe they're on the audience, I'm not sure. And also to all of our sponsors, especially QuakeCoRE, White Trust, who made the research possible, and everyone else. We hosted about 200 practitioners from the industry, and they visited our tests. And we also, throughout the research, we did several of seminars of this kind, presentations, and so on, reflected on the comments. So thank you for all involved. And I'm happy to answer any potential questions. Thank you.
Thank you, Ashkan.